Hi, everyone. Welcome and thank you for joining us today for our EAStalk webinar with Martin Føre. Martin will talk today about precision farming, artificial intelligence, and big data. My name is Anna Vickovic, and today I will moderate this session. EAStalk webinars last for 45 minutes with 30 minutes of presentation time and 15 minutes for questions and answers. At the end of the presentation, you can give all the burning questions to Martin. Martin Føre is currently working as an associate professor at the Department of Engineering Cybernetics at the Norwegian University of Science and Technology in Norway. While taking his PhD, he was working part-time at SINTEF, and following his PhD defense, he stayed at SINTEF as a research scientist for 8 years. Before returning to the university in 2019, his main research area is the application of cybernetics methods to challenges in aquaculture industry. Some of the highlights of his research career thus far are his work of fish modeling and his role in defining the precision fish farming concepts. Martin will focus today on the applications of methods within precision farming, artificial intelligence, and big data in intensive aquaculture. He will give a brief introduction to the scope and focus of his talk. Furthermore, he will account of the status of these areas, but outlining examples of current application within the both industry and research. In the end, he will briefly summarize his predictions or expectations for the future development in this area. First, I would like to thank you, Martin, for accepting our invitation to share your work with us. If you're ready, we can start now with your presentation.
Yes, thank you, Anna.
Thank you, Martin.
Yeah, you've said, so you've introduced me now, so I don't have to say who I am, but I can say it again. My name is Martin, and I work at NTNU. I will talk to you about precision farming and artificial intelligence and big data in intensive aquaculture. I've written this presentation together with two of my colleagues, Morten and Jarve, who are both working at the same department as me. Okay. Let's look at what I'm talking about today. So first I will have an introduction where I'll introduce the three terms that are mentioned in my title: precision fish farming, artificial intelligence, and big data. And the reason why I want to do this is because especially the two last ones, artificial intelligence and big data, they can be interpreted in different ways. So I would first just like to say something about what I associate with these terms in relation to these talks. Then I will go on to talk about the state of the art, where I will look at how these three, you could call them technological areas, are currently applied in aquaculture, both on the industry side, but also on the research side. So I will try to elaborate a little bit on the current state of the art there. In this segment, I will style it based on the structures of the precision fish farming and different phases with the observe, interpret, decide, act. Kind of phases that I'll get more into that later. In the end, I will present some future prospects where I'll first talk about how I envision these technological areas can be key enablers in increasing our ability to control existing farming endeavors, but also talk a little bit about the role I think these areas will have in preparing us for taking use of the new future concepts for fish farming production that are emerging currently. So, starting with the introduction, I'm starting in very familiar territory. I'm starting with precision fish farming, or PFF for short, as we say. Precision fish farming was a concept we sort of developed over the last years, based on the motivation that we would like some kind of framework or philosophy or something to approach how we can apply technology to aquaculture operations with the aim of increasing the ability of human control over the biological production process. So this was our aim, and we started looking into how can we do this in a structured manner, because if you just say use technology in aquaculture, it's a very open question how you can do this. So our first choice was to look at how operations and management routines are done in aquaculture. And what we saw was that you could actually envision that you could structure all operations and management routines in aquaculture into 4 different phases. Almost irrespective of what kind of operation you're doing, you would always first observe the fish. Observe the fish, see what the fish are doing, how they look. Based on this observation, you would then start to try to interpret what this means in terms of the state of the fish, which is the second phase on the top left there. Following this, you would use these interpretation and these observations you made as a foundation for making decisions on whether or not you should conduct some kind of action on the cage or on the fish directly. And then you go back to observing the fish to see if this had the intended effect on the state of the fish. It's not a very new way of thinking. This is a way of thinking that you will find many places, even in defense, in production technology for cars and so on. But still, it's a useful exercise to find out how you can decompose operations in aquaculture in order to identify small, concrete things that you can try to apply technology to improve. Because all of these phases have been mainly manual and experience-based in conventional aquaculture. We believe technology can be useful for improving the objectivity and the repeatability of these different things. I get more into this later on in my talk. A little bit of history of precision fish farming. As many of you might suspect, the roots of precision fish farming is in precision livestock farming, or PLF, which is a more established term for a similar kind of philosophy or framework or approach in terrestrial livestock production. And actually, this was a key element in us developing precision fish farming, because we included a couple of co-authors in our first study on precision fish farming that were well-established figures in the precision livestock farming industry, because we wanted to adopt these thoughts that they had developed for livestock farming over to fish in the proper manner. However, historically, there are even older roots for precision fish farming, and these we can find here in Trondheim in SINTEF and NTNU, because in the 70s you had lots of activity on this area. You had professors and research scientists that did things then that we would today label as precision fish farming, actually. In the picture here that you might see, it's a safe carrying an acoustic telemetry tag, and this was in 1975. So they were already doing things that we now consider a part of precision fish farming back then. They were modeling fish as well. And all of this activity was led by the old Professor Jens Balken, who was at my institute back then. But it's not until now that we've been able to fully adapt these thoughts and start applying these to aquaculture, because now we have the technological readiness, because they didn't have that in the 70s. The second term I would like to explain is artificial intelligence. This is a term which has become more and more of a household object today, both in industry and in research, obviously. Actually, a colleague of mine said the other day that artificial intelligence was now like bread and butter. You will meet it everywhere, and everybody takes it for granted. In my youth, I associated artificial intelligence mainly with these Terminator-esque robots that you can see on the right-hand side, that you had robots or artificial life trying to mimic what the humans are doing. Of course, this is a very narrow definition, and a possible definition you can have today is that artificial intelligence is basically any kind of approach where you make computers or machines do tasks that are perhaps less suitable for humans to do, but also that do tasks without direct human supervision. So they do the work themselves, which is kind of a more open definition than my Terminator-based definition in my youth. So basically, you make computers do things that are often less suitable for humans to do. For instance, finding relations between inputs and some kind of output variable you're interested in. it's a very broad area, and many things are just pulled into artificial intelligence. It's a very hype, really, to label stuff artificial intelligence as long as you have a computer there. But essentially, you can say there are some methods that are well established that are much used in both research and science now. You have neural networks and deep learning, machine learning, etc. All of these kind of methods where computers are working the data independent of a human operator. This here figure shows, in the middle, shows an illustration of how a neural network works inside a computer. It's made by one of my master students, Christian. The idea is that you have an input layer where you put in some kind of sensory data. It could be, for instance, pixels from a picture that you put into as an input to the system. Then the computer finds all the different links and weights between the different inputs. So that on the end, on the right-hand side, the computer system can output some kind of interesting parameter. For instance, you could feed in pixels from pictures taken in a cage on the left-hand side, and then what you get out on the output side could be, for instance, the frequency of eyes in the pictures or the movement of fish or particles in the picture, which are typically quantities that artificial intelligence is very well adapted to find because it can work independently and do lots of tedious work. But a human might not be so well suited to inspecting all the pixels and trying to find these things. As I said, artificial intelligence is a very popular term. It's been used for many, many years and probably hasn't reached the peak even in its popularity curve. It's used in many different industrial sectors and disciplines. The third topic I will talk about is big data. This is a little bit further from my personal expertise, actually, but I will have it to go anyway. It's an even more fuzzy term, I would say, than artificial intelligence, because what is big data? It's just like an adjective and like a word. But there is a definition, and that is big data, or a big data set is a data set that is too large and too complex to handle using conventional handling methods, meaning they're too large and too complex to handle on a laptop computer using conventional software. It's a nice definition, but bear in mind that this also indicates that what big data really is a moving target, because if you go 20 years back in time, you would probably consider something then as sort of a big data using the same paradigm, which we now wouldn't consider big data because the computers and the software has been much more powerful now than it was back then. But of course, it's still interesting to look at methods of handling data sets that you can't handle using conventional methods, irrespective of what those conventional methods are. So the way people typically define big data is that it's a big data set if it has a volume, meaning an amount of data, that is larger than usual. It has a variety, meaning a variety in types of variables or parameters of the different data sets, that is larger than usual, and also that the data arrives at a higher velocity than usual, that the data speed into the system is higher than you would expect. In addition, some people operate with two more terms, which are veracity, meaning that the data that you use can't be considered a big data set unless it is verified, that you know that the data are good, that it's not trash data you're working on. And of course, the final one, the V for value, meaning that the data set you have shouldn't really be considered a big data set if it doesn't have any kind of value with respect to what you're actually observing. So this is like the paradigm of the V's, as they call it, the people working with big data, which can be a useful guideline if you're wondering if you should employ big data techniques or not. Handling big data requires some different approaches. It requires high performance hardware. That's the conventional way, that you, instead of using a computer, you can use a server park as pictured here. But perhaps more commonly, it's starting to diverge towards people using cloud computing instead, that you load up your big data set to the cloud and then you start using methods on it in the cloud. And as for methods for processing these kind of data, of course, if the data set is too big to handle on a computer, it's too big to handle by a human. So you often have to resort to those methods we label as artificial intelligence methods. Big data is a more recent term than artificial intelligence, but still we're seeing more and more use of this term as well in the industry today. So, with that in mind, how about aquaculture? What's the status of the application of these kind of things in the aquaculture sphere? As I said, I will now go through the different phases outlined in the precision fish farming concept, and that's just to structure this part of my talk in a way that is, I think is more easier to communicate. Starting off with the first phase, the observe phase. The idea about the observe phase is that you observe the fish, you see what are the fish doing, how do they look. Basically, this is an operation that was conventionally done by fish farmers, either walking around the cage, looking down into the cage, or using submerged cameras to look at the fish, but still manual observations. So this is an area where I think we have gotten quite far today, especially in using methods such as machine vision, which is basically using artificial intelligence methods on camera streams. It was supposed to be a video here, but it doesn't work, but that's no worries. In machine vision, you use methods to derive numerical values from video pictures. So instead of providing a series of pictures, you provide a series of numbers. And this is an area where you often use methods from artificial intelligence, such as neural networks and so on. And in these two pictures, you have on the left-hand side the application of machine vision to derive movements in the pictures, which are then related to the movements of the fish. And on the right-hand side, you have the application of these kind of methods to identify different parts of the fish automatically. So you can identify the eyes, you can identify the head, the fins, whatever. So these are examples of methods that are not only applied in research, but also in industry. The picture on the right there is actually from an industry project that's ongoing now, where they're deriving individual-based data using cameras and artificial intelligence. Echo sounders and sonars is another way of quantifying what's happening in the cages. And this is also increasingly being used in aquaculture, mainly to observe the distribution of the fish, as you can see here, where you look at the fish using active acoustic methods. The way they work is that they send out acoustic pulses, and when that acoustic pulse hits the fish, it's reflected back, and then you get a picture of how the fish are distributed in the sonar beam, as you can see on the left-hand side there. This is an area which I think is very unexploited today, because I think there's so much more information you can get from these echo sounders other than just the distribution, as you can see on this colored plot in the middle. So I think that's a great source for information. A third method of getting data or quantifying data on the fish in the sea cage is the use of biosensors and telemetry. And this is a different method because you have to equip individual animals with electronic devices that either transmit data acoustically to a receiver, as you can see on the left-hand side there, or that store the data inside and you can read it out after collecting the fish again. Now this gives you the ability to measure the individual history of the fish, and therefore is a more sort of different approach to collecting data in the cages than the other two who target more groups. The example data you can see on the bottom here is individual swimming activity measured with telemetry during a crowding and delousing event. So we do have some tools to quantify what's happening in the cage. How about interpreting this data? That's important. Of course, you could use these data as they do today and use experience to interpret these data and to see if you can from this glean how well the fish are doing, or you can use more technologically based methods. One of my main research areas, as Anna mentioned, mathematical modeling of fish. This again was supposed to be a video. I don't know why it doesn't work now, but okay, bear with me. This is a mathematical model that simulates individual fish behavior in a sea cage. And what the mathematical model basically is that you take all the knowledge you have about the system, collect it together, and then you make equations trying to mimic these things. So for instance, if you have a description of how the fish respond to feed, you try to make equations that can predict this kind of response. And when you put this together in a common model describing all the aspects of the animal or the phenomenon you're observing, you can predict how this system will respond to certain conditions. So if you have such a model, you can predict how the fish are behaving in a sea cage. And if you then compare these predictions to the real-time measurements you make using sensors or other devices as described on the previous slide, you can get an impression of if the fish are doing as expected or if they're doing something else which might indicate that they are not in the best of shape. That's one way of doing it. Another thing I should mention is the use of more advanced interpretation tools. This is a picture from an industry provider in Trondheim called Autoscale, who use structured light to illuminate fish they're filming, and then use this structured light and advanced interpretation to estimate the size of the fish, which is a good estimator of the state of the fish, I guess. But I believe that the largest potential lies in the combination of these two works, combining real-time data with mathematical models in what we call estimation in cybernetics. It's a very common method where you combine mathematical models with real-time data and thereby enabling you to observe things that cannot be observed directly using sensors. You can illustrate this here by, say, that you combine data from real-time data from a computer vision system measuring, for instance, speed, with data collected by acoustic telemetry tags on swimming activity. And then, if you can combine this with a mathematical model predicting the behavior of the fish, you can create estimators in the same way that they've done it in many other industries to observe the things that you can't observe directly with sensors in the cages. So you can get a more holistic picture of the state of the fish. Even if you're able to do this, and if you're able to collect objective data using technology in the cage, and interpret this using a combination of real-time data and mathematical models, deciding what to do next is typically still a manual process, and it will probably be that for many years, because if you want to automate the decision thing, you need to be sure that the data that you should make these decisions on is really, really good. One easy step forward would be to combine different data relevant for a specific operation, for instance, in a common view. Because traditionally it's been like you can find the temperature at one place, you can read the oxygen at another place, and you can count the lice out of the cage. But looking at these data at the same time while making the decisions could be a key. For instance, in delousing, could be a key element to not only look at the lice count, but also look at other parameters as indicated here. For instance, the dissolved oxygen level, the mucus layer, health score, etc. And I think you have some industry actors moving in this direction now, trying to combine the data in a common view, making decisions easier for the farmer. If we get to the point where you can really rely on the data and the interpretation of the data done by machines, we could get to the point where you can start adapting the methods emerging from artificial intelligence today, such as case-based reasoning, which is a method where you combine real-time data with predictive models and with experience-based or experience data to make a system that can actually recommend your decisions for you. But we're still a little bit far from that yet, I think. But assuming that we are able to do that, that we can make decisions based on a more holistic, objective picture of what's going on in the cages, we can quantify what's happening, we can interpret this based on technology, we can make decisions based on this sort of objective and holistic foundation. How can we then realize action? How can we enact things in a better way using technology? Already we have some technology in this area, actually. You have feeding systems that are automated. You can just say how much feed you want to deliver to the cage, and the system handles all the transformation of this signal into the control signals to the blower systems or whatever that delivers feed to the cages. You also have ROVs, such as the one here, remotely operated vehicles that can be used for inspection and control. You have AUVs that you can use to inspect stuff. You have several different tools that are used to a certain extent to automate operations in cages. And you also have winches, such as this one from Aqualine, which is mounted on the ring of a cage, which can enable you to winch up the net cage without having people actually pulling on the cage, which is a great improvement in terms of health, safety, and environment aspects. So you have a whole lot of tools already, but I think that we should strive towards developing new vehicles and tools. This video on the right-hand side was supposed to show a snake robot. I'm not saying we should use snakes in cages, of course, but this is an example of how it's possible to think outside the box when you're talking about vehicles to automate operations. This was a snake robot developed by NTNU and Syntec over many, many years for subsea operations. And it was based on some specific criteria and needs. And I think that we should start looking at developing new vehicles and tools adapted to be able to be used in flexible cages filled with living organisms and do operations for us there. Because I think we need to appreciate that the setting in a sea cage is quite different from, for instance, an offshore setting, which is where the ROVs come from, or even a defense setting, which is where AUVs come from. So we should stop using tools developed for other sectors and start thinking about developing our own tools for these kind of things. Having said that, I move on now to the final part of my talk, where I will look more into the future. Some might call it speculations. I hope it's more similar to predictions. I don't know. First of all, how can we envision that we can increase the control we have on the biological process given the current farming regimes? I mean, we have fish farms operating in all over the world. How can we use technology in an efficient way to improve our management and operation of these farms? And especially, how can we use methods from artificial intelligence and big data to do this? First of all, I would like to show this one, which is Ocean Farm 1. This is a huge fish farm outside of Trøndelag, managed by SalMar, but instrumented by Kongsberg, who put in several upward-looking echo sounders. They put in several submerged cameras, passive hydrophone, many different types of equipment. Of course, this generates a whole lot of data, but exploiting these data isn't that simple. That is because I would argue that the data stream from this cage is can be defined as big data. It is possible, and I would believe it likely even, that more and more farms would try to exploit the increasing possibilities in technology, and that you would see more and more instrumented fish farms producing more and more data, thereby increasing the need for artificial intelligence and big data methods, as far as I see. But for me personally, I need to, again, talk about the estimation of fish states, because I think that is probably the closest approach, or the closest or lowest hanging fruits, so to speak, now. We already have many systems for us observing the fish, as I've talked about earlier. I think time has come to try to use sensor fusion techniques to combine these data types and combine this with mathematical models so that we can observe the fish that we can't observe directly through the models coupled with the sensors. As indicated in this figure with the green fish that we don't observe directly, but perhaps you can say something about it by combining these observations we have with models. And finally on this slide, it is important that we always also think about human presence at fish farms. It's becoming increasingly difficult in terms of weather and conditions and farm locations to have people non-stop at the location. So using technology to increase the autonomy level is also something we should strive for. As an example, I can say that it's a snowstorm outside my window now. It's quite normal for May, but of course, if that happens out on the fish farm, you don't want to be there. Then you would like to have some kind of system that could ensure that the fish are fed while you're gone. So that's traditional farming methods that we have today. What about future developments? I've already talked about this massively instrumented site outside of Trøndelag here in Ocean Farm 1. But I believe that we won't just see the need for using big data and cloud solutions to process the data from one of these farms, but perhaps we need to look at more sort of holistic views of regions, that you can process the data from different regions at one time. And together using big data methods. And this could help us show, or perhaps it could help us uncover ways that we can do things more efficiently or safely by using the data that we collect from these farms together. It could also help us analyze how the growth is developing in region level instead of just at farm level. And of course, you have the more complex units that are emerging now. You have this example, which is the egg from movie, which is a closed containment unit put out in the sea. It's never been used before to raise fish, so I think it's my belief, at least, that it would be very important to also be aware that we need to use technology to observe the fish in these facilities, but also to try to control the process in these facilities in a more close manner, because we don't know really how production will go in totally new production units. And the same applies to the land-based recirculation systems that are picking up all over the globe now. And finally, I would also like to mention satellites, because that's a very interesting topic, I think. Because I was chairing a session in Berlin in the EAS conference there in 2019, and there was a person from IBM talking about using satellites as a predictive tool for fish farming, or for aquaculture in general. I think it's very interesting that you get this, that satellites are now becoming more of a household object in also aquaculture. I think it has to do with the satellites becoming actually cheaper to just make and send up there. So this is also an area where you can collect huge amounts of data by using, for instance, hyperspectral imaging, and that you can probably use to predict algal blooms and other things. I don't know, but I think there's a potential there. And thank you. 1 minute, 47 seconds over time, but that's okay, I hope. Thank you.
Yeah, it's definitely okay, Martin, and thank you for giving a fantastic presentation and for explaining us a bit more in detail about big data and AI. We have a question. It was a really good presentation. We have a question. Let me just check it right second. So, how the artificial intelligence or big data-based fish farming is going to make the farming truly a sustainable fish farming?
Well, that's a big question, isn't it? But yeah, I think it's my belief that as long as the ability to make something sustainable, it depends on your ability to control the process, of course, and the ability to control the process always will depend on the ability to observe the process. So I think you need to observe and be able to sort of monitor the process before you can start talking about making it sustainable. But I think it is possible. It will give you a better control of the production process, and it can, for instance, be used to perfect the amount of feed you use or prevent escapes. All of these things that have a negative effect on the sustainability of the industry, as far as I'm concerned. And also you can pick up on lice outbreaks earlier, and you can treat the fish earlier so that the lice don't spread to wild fish, for instance. There are many things that you can see in the wake of increasing the control of the production process that will contribute to sustainability, as far as I'm concerned.
Okay, thank you. The next question is, so what are the prospects of 3D printing and drones to go for a dangerous diving in the sea for the aquaculture-based data generation, more particularly the low-cost sensor for aquaculture?
You said 3D printing?
Yes.
Okay. Yeah, but drones, at least, that's something I think will become more and more common, especially for inspection, and cheap drones at that, because if you can produce more, the volume, of course, defines the costs. And if you're just going to inspect, you don't have to have a very expensive drone. I'm pretty sure that this is going to be one of the earliest things you'll see, that people are going to use more of these things because they're getting quite cheap now, and it's easy to use. And of course, I think that's, at least in Norway, that's been one of the big challenges when you have to use divers, because it's a very risky place to dive. So using drones instead of divers is one of the sort of earliest things I think you'll see, because it's there's so much you can do with the drones. Of course, the repair and stuff like this is still difficult using remotely piloted vehicles. That's definitely observing, monitoring stuff, biofouling, holes in the net, detecting stuff like this. Yeah, I guess that's
So it could be possible to implement it.
Yeah, definitely. I think it's already happening now. You have more and more people, at least in Norway, starting to use these drones more regularly as more of a everyday tool than a big RV.
Let me just try to connect Jennifer. Jennifer has a question for you.
Yep.
Jennifer, can you hear us?
Yeah, can you guys hear me too?
Yes, we can.
Okay, perfect. I was just wondering whether those technological advancements, whether there's applications for fish welfare too. So, for example, you mentioned lice detection, so I could see that being a really big thing. But is there something else where you can maybe measure, for example, fin abrasions or things like that with those technologies?
Yeah, absolutely. This is something I could probably talk for like 45 minutes about, because this is actually one of my main motivations to be in this business. It's to use this technology to make the fish have a better life, because we have to consider we're actually working with animals here. So welfare is definitely the most one of the definitely most important challenges, I think. And as you said, with fin abrasions, we've used it is a bit more difficult, but there has been done research on detecting wounds on the fish using cameras. My particular research has actually, I don't know if you can see this thing I'm holding up now. It's it's difficult to see, I guess. This is a tag that you can surgically place into the fish, which can measure the heart rate of the fish. And this is something I've used to try to assess the stress of the fish during, for instance, crowding, because I think one of the most important challenges we have as researchers is to figure out how they can do operations without hurting the fish. And crowding, where you raise the net, press the fish together, and try to pump them through a delousing system or whatever, is a very demanding and taxing activity for the fish. So my main research interests are actually to apply this technology so that we can better observe how the fish are doing and what we can do to make their lives better. Because, yeah, we need to make money, we need to have good growth, but I don't think we should do that at the cost of animal welfare. So, yeah, definitely. And computer vision especially, also telemetry, I believe that we could use also in time, you could also use sonars and those kind of tools for more welfare-related observations, but it's a little bit more difficult. It's easier to envision that you can detect wounds directly on the fish using cameras, for instance.
Thank you, Martin. Jennifer, do you have any other questions for Martin?
Can you hear me again?
Yes, we can.
No, I guess my question to that would be, because we as an organization work mainly in Asia, I think someone else asked that question too, but in terms of like economic viability in countries where there's just usually not much money left for technology in aquaculture, is this still a viable thing to do, or is there like minimal viable products they could use or something?
Yeah, I think if you look at, because that's a challenge, because if you look at Norway and Scotland and Canada, it's a different thing than in India, for instance, and where you have a different economies. These kind of things, I mean, the tags I was talking about, that's probably one of the worst examples, because these are quite expensive. But I think solutions based on camera and artificial intelligence, they don't need to be that expensive. They can be quite cheap, because it's an area that has a very high throughput. You don't need extremely expensive equipment to do this. And I think these solutions, which are in fact the solutions that are developing fastest, could also be applicable to many other types or many sort of lower cost kind of aquaculture industries.
Thank you, Martin. Thank you, Jennifer. The next question we have is from Sebastian. Sebastian, can you hear us?
Yes, I can hear you. Can you hear me?
Yes, we can.
Hello, Martin. Thank you for a great talk. I just wondered if you could give us a couple of examples on precision fish farming that's happening at the moment and what the highlights and the lowlights are. And I'm also particularly interested in what's going on with measurements for biomass at the moment, because that's something really fundamental for any type of production facility.
Yeah, those are also big questions, of course. I could start with the beginning. You said precision fish farming endeavors going on. Well, we're trying to introduce things in Norway, but of course in Norway we had the problem that things are going well for the farmers, so they don't really have to invest in anything. They just make money anyway. But we have this thing that I showed you with the Kongsberg farm, Ocean Farm 1. That's probably the one that's closest to being a precision fish farming case. But there is one place where they're doing where they have closed the loop, and that's in Italy, because there was this presentation at EAS last time from Italy about trout farming in raceways, and they were actually starting to close the loop for real. So they were focusing on oxygen now, but I think this is a very important step. They were starting to use estimators. They were starting to try to use models together with sensors, and starting to try to use this to control the oxygen additions to the water. So I think that's a very interesting case that I hope we'll see more from in the future. and then we were talking about biomass estimation. Yeah, that's always a challenge, and it's been a challenge throughout all my career. And I remember I was part of a project at one point where we were supposed to develop new technology to do this, and the industry was then demanding that we should have a precision of less than 1% error in the number of fish in a cage, which is quite hard. And we didn't achieve the goals as well, but there's been so many attempts at solving this challenge. Now I think we have some actors starting to pan out. You have these biomass frames that you've probably seen, which use light. They emit light from the sides and they scan the volume of the fish, and then thereby are able to estimate the weight of the fish. And you also have these solutions based on stereo video, such as the one you saw with the structured lights from Optoscale, where they're using structured light to measure the size of the fish. The challenge about both these, though, is that it depends on where you place it. If you place it at a certain depth, you will see the fish swimming at that certain depth. And you can't place it all over the cage because there wouldn't be room for any fish. So it's kind of a challenge. It's a point measurement that you need to be very precise in how you place. One of my hopes would be that you could use acoustic methods to do this, that you can use echo sounders or sonars to scan the entire volume of the cage and then get a picture of the volume of fish, which multiplied by a density factor could give you a measure of the density. No, the biomass, I mean. That's the only sort of directly feasible solution I can see for these huge cages that we operate with now. Because, as I said, you know, all visual-based methods and such is just going to be a point measurement anyway.
Yes, Frank, you know, it's particularly difficult to measure the biomass. I'm coming from a time where I was working on a land-based farm, and you know, some things were remarkably difficult to do just simply to get a biomass measurement. And in land-based, you really want to know your biomass quite accurately, because any feeding, overfeeding, is really going to impact your water quality. But already there on this land-based farm, we were generating a lot of data, be it how a pump was running and water quality data. So in some scenarios, there's already a lot of data being generated, but we weren't using it to the extent that we could. And a really interesting area for the future, and hopefully some changes come soon.
Yeah, because I think this is sort of what we wrote in the. I think we wrote this in the precision fish farming article as well. That the biomass challenge is sort of like the holy grail, because if you can solve this, you can control things in a much better way because you know what you have. Because this, where I come from in cybernetics, people work a lot with oil and gas and all inert objects, you know. And in those cases, it's easy to measure how much do you have. You know? So it's easier to implement these kind of methods that I'm talking about, the estimation and whatever, in those situations. But I try to stress all the time when I'm talking to my colleagues that biology is so much more difficult. Because it is.
Yeah, definitely. But that keeps it interesting.
Yeah, it is.
It'd be nice to see some advancements in that field soon.
Yeah,
definitely.
I hope so.
And I think when they come, they'll be heavily used, I imagine.
I hope so.
Thank you.
Thank you.
Thank you, Sebastian. Thank you, Martin. We still have a lot of questions, but let's do 2 more questions before we wrap up. Is it okay for you, Martin?
Sure.
Perfect. So let's see a question from Juan Antonio. Juan Antonio, can you hear us?
Yes, can you hear me?
Yes, we can.
Yeah, thank you very much for your presentation. I really appreciate it.
Okay.
My question was in the same direction as the previous one. It's about the importance of being able of estimating real biomass, and not only the average weight of the fish populations or shrimp populations. I guess it's been already answered. But I also wanted to underline the importance of having this measurement in an automatic way. We are working into that technology. There are several startups working into that. You gave your opinion. So thank you so much.
Thank you.
Thank you, Juan Antonio. Another question we have is from Wayne. So can you provide any comment on the operational experiences with the large offshore cage systems, fish growth disease and parasite management and treatment?
That's a very good question. We don't have that much experience yet, but what I've heard is that they have had less lice, it seems. This is just based on very few cases. They've had good growth, of course. Actually, they've had very good growth. As you saw in the Ocean Farm 1, it had a better than expected growth, which is interesting. You also saw some behavioral differences that we didn't know would happen, because I think it's because the cage was bigger. But operationally, it's of course much more difficult because you have to go out to much rougher seas, and they've had some challenges with that, just getting on to the farm and such. So it's a little bit mixed, but I think the biological prospect of going out there seems quite promising, really. That's what I've heard anyway. I haven't read these reports in detail, but I think we'll start looking more into them in the coming time, because now we're starting to get some data from those places.
Perfect. Perfect. So I'm gonna now wrap up the webinar. I would like to thank you all for participating in our webinar with Martin. The video of this webinar will be posted online soon. Our next webinar will be on May 26th with Pantelis Kousalaki. He will give a presentation on the phage therapy as an alternative treatment in aquaculture and applications in fish hatcheries. Please make sure to share our EAStalk with your colleagues and your friends. And as I said before, if you would like to propose or if you have any questions for Martin, let me know. And if you would like to propose any topic for a future webinar, please let me know. Thank you once again for joining us today, and thank you, Martin, for giving amazing presentation.
Thank you.
Thank you.